Thank you. Good afternoon. I said that we'll be talking about really the next generation of electrical links or electrical SerDeses and optical links in order to address the 100 terabit switches. So I'll start with an introduction that's based on our experience with the coherent in the coherent space and the move to pluggable, how we can leverage that into the IMDD application and the electrical links. So we look at the test bed where we assess the SNR versus the link on the electrical side. We extend the analysis to the optical and look at the SNR versus channel and chromatic dispersion. And finally, we'll conclude. So the 400 gig ZR is enabled really 400 gig in a small form factor QSFP-DD. It's effectively in a USB stick. You are getting a 400 gigabit per second that can reach 140 kilometer in a sense. So when we first introduced at Nortel, the first coherent at 40 gigabit per second, the power was, astronomical. And then the size was big. It was unimaginable that we'd be able to fit all of that processing in a very small, form factor. At the heart of this, QSFP-DD is the DSP chip. It is a 7 nanometer DSP chip that has high-speed A to Ds and high-speed DACs, that has, DSP and FEC, modulation and correction and carrier recovery and all of that. So, but it's on top of that, we with co-packaging and co-design of both the silicon photonic, the DSP chip, the TIA, and the driver, we managed to simplify this, and put it in a very small, HDBU or substrate. We call it the quartet, where we have the DSP and then the silicon photonic and the BiCMOS chip for driver and TIA. And the benefit of that, we get very nice electrical, behavior. The characteristic of the channel becomes more predictable. The loss, at the frequency, or it's 0.4 dB. So we see that, several advantages to this co-integration of silicon photonic and CMOS and BiCMOS. During the design, we optimize for spectral shaping. We optimize for required OSNR, for power for sure, for link and WDM propagation, for density and throughput, and resiliency with respect to temperature and variability in the launch power. Plus, it has multiple engines. It has an engine that can go, the long reach, hundreds of kilometers. So we can see from this data that, that the limit for the OSNR, as defined by the, by the OIF, is 26 dB, and then we are well below that, and that's a good number. And we see that number does not change with the TX power, TX output power. But at the same time, on the right curve, we are seeing also that the performance is steady with temperature and with TX power. So that's effectively, so then it opens the door, with this best-in-class performance and power. We are the only, plug that meets the 15 watts for effectively all of this plug. So 400 gig for 15 watts. That's unimaginable, a couple of years ago. So we said, okay, how we can leverage this? There is a convergence between electrical SerDeses, IMDD solution, coherent solution for short links and long-haul coherent solutions. All of them are converging and using high-speed ADCs and DACs and power-efficient DSPs. So we are using this to do the assessment of how we can use the 7 nanometer chip for 400 gig, which is 100 gig per dimension for the coherent, in a 200 gig application IMDD. And, to our delight and surprise that, we can achieve that. So we just encode the data, offline. In PAM4, PAM6, and PAM8, we do the digital precompensation. Then we just load it in the memory of this chip, and then we just do the propagation across the channel. We receive it at the other end by high-speed sampling ADC, and then in a memory, and then we do the post-processing, in this case, for the intent of the testbed. We decided to operate at 75 gigasample per second, so we capture the transfer function of the link, and we use LMS to estimate the channel impulse response, and we invert that, and the inversion, is we maximize the post-equalized SNR for this. So with this data, that's the type of, eyes that we are receiving if we are talking about PAM4, PAM6, and PAM8. And in the table below shows different channel attenuation. Here, we are not doing any CTLE. Most of the compensation is done digitally, is done effectively at the ADC. So if we have the peaking function, because in this setup, the peaking function is in the BiCMOS, and we are not using the BiCMOS. We are using only the CMOS for this. So we can achieve better, but even with that, we can achieve 25 to 30 dB channel loss with this. While for these links, we're talking about VSR, we're talking about 16 dB links. So, and that meets, the BR target, which is, 1 e to the minus 3. But as you can see, PAM4 is more resilient to, to SNR degradation, or requires less SNR than PAM6 and PAM8. And we see also that the MLSE is able to improve the performance of the system. So we took the analysis a little bit further, and we just looked at how we can leverage that in an optical link. So in this case, so we use the transmitter, but the processing of the optical side is done offline. The assumed transfer function of the modulator is a worst case transfer function, and that's really to see how much, because we are able to attenuate drastic attenuation of the channel. So we picked a very bad modulator, and that minimizes the power to drive that modulator. And so we just look at it, how much SNR we'll get with just this type of attenuation, and how much SNR we get in presence of chromatic dispersion. So the red curve is showing that when the dispersion is in band, and could create a null in band. So we need a nonlinear technique to compensate for that. And the green curve shows when the dispersion is out of band, so we need just a straight linear technique to compensate for that. And you can see effectively two eyes without dispersion and with dispersion. Here it shows that it summarizes that the objective of getting 200 gig running 10 kilometer is possible for this application, and that's in line with the IEEE 822.4 assessment for beyond 400 gig study. So 224 with PAM6, PAM4, PAM8 is feasible, and it just for the majority of the application, it will be able to go 10 kilometer. So as a conclusion, a 224 electrical link is feasible, and VSR will be, for channel loss and power can be achieved in this. And we're showing that even our 7 nanometer today for the ZR are able to do that. The FFE and the MLSE can improve the reach of the 224. On top of that, a SERDES, or an electrical SERDES can be used for IMDD 200 gigabit per lambda. And we can use either linear techniques or nonlinear techniques to compensate for chromatic dispersion to extend the reach to 10 kilometers, which is really most of the distance inside the data center. At the same time, we believe that this will enable 1.6 terabit plug at 10 picojoule per bit, and there is a path of a 3.2 terabit per second plug at 10 picojoule per bit and lower even. Thank you.
Excellent. Thank you so much.